Hi, my name is Christiana, and today I'm going to talk about this work we've been doing at Toshiba Research Laboratories at Toshiba in Cambridge, in collaboration with the University of Cambridge and under the supervision of Andrew Shields. So just a quick overview of what I'm going to talk about. I'm going to give a brief introduction before going to describe our entangled LED design, which is the source used in our experiment. Then I'm going to talk about the actual experiment, which is a proof of principle experiment of a quantum relay over 1 kilometer of optical fiber. And finally, I'm going to give out some results. So it's true that these days, quantum cryptography can offer many ways for two directly connected users to communicate securely, using QKD, for example. But when it comes to connecting multiple users, it becomes a bit more challenging. So if we wanted to connect multiple users in a network system, one way to do that would be to introduce a classical node. So we do have our site, our usual site A and site B, and we can introduce a classical node in between, which can receive and resend the information. However, in this configuration, this intermediate node will have to be trusted. So for a fully quantum system, we can have other ways. Some schemes have been proposed, such as quantum relays. So we can have this configuration here, which is what we used in our experiment. We still have site A and site B, but we can introduce a BSM node to perform Bell state measurements. This node can be untrusted. So by using an EPR source that can produce entangled photon pairs, this one here, this untrusted node can perform Bell state measurement, and we actually can separate the photon pairs and distribute it to this node here and this node here. And these nodes can perform non-local correlations. So when this node performs a Bell state measurement, plus a unitary transformation without revealing any quantum information, input qubits from site A can be teleported to site B. And this is what we adapted for the experiment. So how can we obtain a suitable EPR source? There are several ways to produce entangled photon pairs, and one of them is parametric down conversion, and there have been some really nice experiments with this method. In these setups, some driving lasers can be used with nonlinear crystals in order to produce entangled photon pairs. However, sometimes you can get multiple pairs or no pairs, so the emission is not on demand. And this is the main drawback from these setups. So this is what we're trying to tackle by using our entangled LED device. As the name suggests, it's just an LED. It can be electrically driven. It's just a semiconductor device. And therefore, it can be easily integrated within existing technologies. The main plus by using this device is the sub-Poissonian emission that we can achieve. The entangled photon pairs can be produced on demand just by electrically driving the device. And therefore, that's what we've been using until now. If we wanted to have a scalable implementation of a QKD application using such devices, this source could be, okay, not the answer, but a good option. And just a few more details on how we can achieve entangled photon pairs. The ELED bases the operation on quantum dots. This is a PIN structure here. P layer is on the left, and then type layer is on the right. And we have an intrinsic region in between where we have the quantum dot layer. Quantum dots are these tiny little structures. This is an AFM image. And when we bias this semiconductor device, there's current flowing through the device. The dot can capture 2 electron hole pairs. And we have this situation here, 4 carriers, and the dot is in the biexciton state. So through recombination, we can have 2 emitted photons. The biexciton goes first, and the exciton photon that is emitted afterwards. These 2 photons are entangled. And this is a typical spectrum from these quantum dots. This is the actual spectrum of the dot that I chose for the experiment. And this is how a device looks like. These are real pictures. This is a schematic. We have our PIN diode, P on top and at the bottom, plus cavity on the top and the bottom to enhance photon collection. The collection is on top of the device. We can also bond to the device really easily because we have contacts on top. And yeah, this is a normal, usual chip. It has plenty of devices on it, 48 I think. And this is the gold bond that you can see here, but it's on top. It's a microscope image. And the small size of these devices allows us to pulse them and produce a pulsed single photon emission. And this is my favorite picture. It's again the same thing. This black hole is the gold bond, but because for this picture I only selected, I filtered out just quantum dot light. So you can only see these bright spots. These are individual quantum dots that emit light. And this one is the one for the experiment. Yeah, so this is how it looks like when it's electrically biased. So moving on. This is the experimental setup of the quantum relay experiment. As I said before, we have 3 nodes, the sender, the receiver, and the BSM node here. The sender and the receiver are separated by 1 kilometer of fiber, which is distributed across 3 different fiber loops. So we take our ELED device that emits the biexciton photons and the exciton photons, and we separate them. We separated them, this adds up to 700 meters. And we send the biexciton photons to the BSM node, whereas the exciton photons are sent to the receiver node over here. These 2 nodes have a polarizing beam splitter, shown as this fancy beam splitter, and a pair of detectors, single photon detectors, that can perform non-local measurements on the photons. So we have the sender over here, which employs weak laser pulses to encode input qubits. We can choose from 2 different bases, the rectilinear base and the diagonal base. So it adds up to 4 different polarization states. So the sender encodes the input qubits on these weak laser pulses, and we can interfere them with the biexciton photons from here on this beam splitter. We then take the output of this beam splitter and send it to the BSM node, which performs a Bell state measurement in a certain basis. Once the measurement is done, so once these 2 detectors here click, the input qubits can be seen on the receiver output on detector either 3 or 4, depending on the state that has been teleported. All these state calibrations are done using polarization controllers, electrical polarization controllers. So you can see here, there's one in each node, and that's how we set the basis for measurements. And just a quick note on how we obtain measurements from such an experiment. We record 3 photon coincidences. So we have the input laser photon here, plus the biexciton photon. And these 2 we can detect here. And then we have a 3rd coincidence coming from this end here. So we can define tau 1, 2, and 3 as the time differences between these 3 detections. The ones I will be using for graphs are tau 2 and tau 3. And these are the 2 times that represent the difference in detection between this 3rd photon here compared to the other 2 here. So yeah, I hope this is clear. And some more experimental details. I would like to point out that this was the first pulsed teleportation experiment done with this device. It's been a bit challenging, but we can see that with biasing the device with an AC voltage, we can achieve single photon emission in a pulsed mode. And this is shown with this graph here. The frequency of the AC bias voltage was around 200 megahertz. One more thing to note is that for qubit encoding, we used weak laser pulses, and these were tuned to the dot wavelength and frequency. We have to do this because the laser photons and the ELED photons need to interfere on the beam splitter. We need two-photon interference to be achieved in order to teleport using two dissimilar sources. And this is how, and we have confirmed that with this experiment. And finally, I have mentioned that we have used two different bases for sending qubits, the rectilinear and the diagonal basis. We have states DA, diagonal, anti-diagonal, horizontal, and vertical. So the sender can choose either basis to encode qubits in. And this choice of basis was switched during the experiment so that a randomized sequence of qubits could be recorded in the end, just as normal relay setups. Moving on to results. This graph here shows the three-photon intensity, the total three-photon intensity that we obtained from our experiment. As I have explained before, we have these two times, tau 3 and tau 2. And I don't want to spend much time on this. But what you can see is that the coincidences are concentrated in pulses. So they're concentrated into time intervals, which show that the emission has been pulsed. And what is also important here is that there is a dip along the diagonal of this graph. And this just shows the sub-Poissonian characteristic of the emission. And it verifies that we have a single photon emitter. Another important result is the Bell parameter of 2.59. This is the peak value of the Bell parameter that we have extracted from the third order correlation measurements. And from this, we can extract an entanglement fidelity of around 94%. And this is amongst the highest ever achieved with quantum dot sources. This is again a G3 measurement with quantum relay fidelity. No, it shows the average relay fidelity from all four polarizations. And this is how we assess the performance of our relay. What you can see here is that at time 0, but it's not very obvious. So the high fidelity points are concentrated in this area. This is time 0 when teleportation occurs. So the maximum value that we could extract from these results is 90%, a teleportation fidelity of 90%. The individual basis fidelities are 95% for the rectilinear basis for H and V states, and around 85% for the diagonal basis states, the D and A. And these fidelities are really high for such experiments. So again, this is the average fidelity, average teleportation fidelity from our relay. It's a cut-through section from the previous graph that I have shown. And as you can see, the high fidelity points are concentrated here around time 0, whereas here it reduces to 0.5, which basically means random measurement outcomes. So with these high fidelities, we have shown that the sender and the receiver have shared information in excess of any information held by an eavesdropper. We can also see the threshold for quantum teleportation here. It's 75%, and we have exceeded that as well. We also defined the bit error rate to be 1 minus the average fidelity of the relay, and it comes out about 10%. So there are known error correction protocols that can correct for up to 20% error. So we have exceeded this threshold of 80% fidelity. But we also consider an efficient 4-state BB84 error correction protocol that can correct for up to 11% error rate. So the threshold, the fidelity threshold, comes out as 89%. And using this protocol, we can extract a security fraction of 0.11 bits per detected photon. So we can see how this experiment can fit well with existing QKD protocols for a real relay application. And finally, conclusions. We have shown how entangled LEDs are a practical quantum source with fundamental advantages, and I'm referring to the high entanglement fidelity and the sub-Poissonian characteristic of the emission. It was also the first time entanglement has been distributed by a quantum dot source over a distance of more than a few meters. It was 1 kilometer of fiber. Usually in these setups, they are only in the lab, and yeah, it's just a few meters of distance between the two photons. We have also shown how the average teleportation fidelity has exceeded the quantum limit for quantum teleportation and the threshold for BB84 error correction protocols. We have also shown that quantum teleportation and quantum relays can be used to extend quantum networks beyond dedicated links. And finally, with this experiment, the ELED and the teleportation performance is sufficient for preliminary applications. And for more details about this work, there is a preprint on the archive. And with this, I would like to finish. Thank you.
This paper is open for questions. Yes, Nicola.
Does your ELED provide naturally a spectrum of both temporal and frequency similar to the weak laser pulse, or do you need to filter them?
So it does emit 2 single photons. The only filtering that is being done is using a monochromator to select the emission from the background, but that's all. The only C that I see on the spectrum is the spectrum I showed before.
But the spectrum was looking very different from the weak laser pulse.
Let me go back. You mean this one?
No,
or
the next one, just after that.
Oh. Oh, here. So yeah, for this schematic, I approximated the dot light to be as an exponential. However, in reality, it's more like a void wave packet. So yeah, the weak laser photon pulse is more like a Gaussian, and we adjusted this to fit better with the ELED photons so that they could overlap in order to achieve 2-photon interference for the experiment.
Another question? Yes.
I just want to have some fundamental, understandings on the bi-extons. So, is in your system is it entangled with the X? I mean, the single exton, have the mono extons and bi-extons, or bi-extons has 2 photons and those are entangled to each other?
Oh, I should have explained this better then. Oh, it's here. So the dot captures, these and 2 electron hole pairs. Okay, so the first recombination gives out the bi-exciton. So we are left with 1 pair in the quantum well-like structure, and so there is a second recombination that takes place, and this gives the exciton. So it's one after the other. They come from the same state, so they are entangled.
Okay, so it starts from the same bi-exton states,
yes,
but the radiation process is different, because one comes from bi-exton state and the other is relaxed to a single exton state and then radiated. So there must be some time difference, right?
We consider them to happen immediately after the first emission. So that time is very, very small.
Oh. Thank you very much.
Another question if it's short? Not seeing any? Let's thank Christiana again.